Good morning, approximately 9:41, and here I am at the LaGuardia Airport, Courtyard Marriott. That is the Courtyard Marriott at LaGuardia Airport. It's a national or international airport, Courtyard Marriott. And I want to continue this morning with the demonstration of that amazing 5x12 matrix that has the potential of doing wondrous work with a multi-dimensional application. But before I get to that, we're going to do some electrical electronics problem, demonstrating the Thevenin theorem. Two simple basic problems demonstrating the Thevenin theorem. Now the Thevenin theorem in basics said that any linear circuits of voltages and resistances, if viewed from two nodes in the network, can be replaced by an equivalent resistance, and we call it equivalent resistance R Thevenin, in series with an equivalent voltage source V Thevenin. That is, any linear network of voltages, sources, and resistances, if viewed from two nodes within the network, can be replaced by an equivalent resistance R Thevenins in series with an equivalent voltage source V Thevenins. And so in demonstration letters this morning, as usual, my name is Dolphy Gilpin. Those of you who are interested in my middle name, that's Alexander. And here we are now. We're going to find the Thevenin's equivalent of this circuit. Simple circuit now. So we call that for the B terminal, and this is now the A terminal, resistance 1, and we say like 4 ohms for this resistance 2, 6 ohms, and this voltage source 10 volts, and current is going so. So we find now the Thevenin's voltage. Now the Thevenin voltage is the same as the voltage across this resistance here now, R2. And you know that voltage across parallel resistance is the same, so the voltage across is equal to 10 volts across the R2 terminal. Alright, so V Thevenins, we're demonstrating the Thevenin's theorem now, is equal now to I, R2, because this is the voltage across R2. But I itself is equal to V over R, which is V over the equivalent resistance there now. So I would be equal now, this I, V, which is a 10 volt, over R1 plus R2. And now, that would be I, and we multiply it by R2. And that would give us the Thevenin voltage. So this would now be equal to 10 times 6 over 6 times 6 plus 4, which is equal now to 60 over 10 equals to 6 volts. So there we have now the Thevenin voltage, 6 volts. Now the equivalent circuit is now, let's find the Thevenin resistance. Thevenin resistance would be now we have V Thevenins, we just want it to be equals to 6 volts. and our Thevenin now is to be found. Now our Thevenin is these two resistances, they're in parallel. So we say now that RTH, R Thevenin, is equal now to the short circuit path. So that would be equal now to 6 multiplied by 4 over 6 plus 4. That's equal now to 24 over 10, which is equal now to 2.4 ohms. So the equivalent circuit now, our Thevenin, would be 2.4 ohms. So that would be the Thevenin's voltage, VTH, 6 volts, we calculated there, and the Thevenin's, which is 2.4. So we're saying now by the Thevenin's theorem that this circuit now can be replaced by a Thevenin's voltage, VTH, and the Thevenin's resistance, RTH, and we calculated both the Thevenin voltage and the Thevenin resistance. Okay, let's demonstrate one with a little bit more involved. Suppose now we have a circuit a little bit more involved now. Just another extra resistance to it. And this one now is 12 volts. This is R3, 5 ohms. This is R1, 3 ohms. And this is R2, 2 ohms. We're looking into the terminals now, A and B. All right, we find our Thevenins. So our Thevenins replace this by a short circuit. Or it could be in our mind that we're going to leave out this now and replace it by a short circuit to find our Thevenin. We'll see what the R Thevenins now is equal now to this 2 ohm resistance in parallel with the 3 and the 5. So that would be equal now to 2 times 5 plus 3, 8 over 2 plus 8. And that's equal now to 16 over 10 is equal to 1.6 ohms. Alright, V Thevenins is the voltage drop across this. And we say no, that's equal to I R 2. But I'd say it's equal to V over R. V over R R2. This V is 12 volts. And R2 is 2 volts. And the resistance here now is 2, 5, and 2. Use that to find the I, because I over R. So it's 3 plus 2 plus 5 in series, which would be 3 plus 5 plus 2. So that's equal now to 24 over 10. And that's equal to 2.4 volts. So there we have it now. So this circuit could be replaced now by a circuit R Thevenins, which is equal now to 1.6 volts and V Thevenins, which which is equal now to the Thevenins, just calculated to be equal now to 2.4 volts. So the two problems demonstrating the Thevenin theorem. Let's try to separate them here. As usual. Or we'll take a break and then we'll come back and we go into our amazing matrix, the 5 by 12, discovered and developed and is expected to do some amazing work. So let's take a break and then we come back.